So what I was going to do is demonstrate these new features of the Atlas software. And excuse me, in particular, we've implemented Weyl group representations and special representations and such. So let me get started and share my screen. So I hope we're looking at the Atlas window. Oh no, I think I still need to say present to everyone. Okay, so good. I believe that we are now looking at my terminal window where G is SL2R. And thank you. Where was I? Oh yeah. So please use the chat to correct me if you're not seeing what I'm claiming you're seeing or whatever. If we get lost or confused, the way to interact with me is by chat, since everybody seems to have that going. Okay, so let's start really slowly. We'll just do SL2R to get warmed up and then do something a little more interesting. So G is SL2R, and you need to define a block. And so you say B is block of G dual quasi-split form of G. And those of you who've been using the Atlas software may or may not remember, excuse me, there's two ways of defining blocks. The old-fashioned way, where you specified a group and a real form of the dual group. And then there's the new way in terms of parameters. And this functionality is in terms of the old-fashioned way. There are ways to convert back and forth, but I'm not going to get into that here. We'll just be using these blocks. And this block, I forget if this command works. There it is. This is the block that we're talking about. This has three representations, two discrete series and a principal series. And now one of the things that's new is that we have features for dealing with characters and conjugacy classes in the Weyl group. So the first thing that you do is you set up the conjugacy class table of, hang on one second. You set up the conjugacy class table for this group. So you say set CT is equal to a W class table of G. Okay, so now this is a data structure that's a little bit complicated. You usually don't want to look at it directly, but I'll just show you so you see. It's got all this stuff in it. And there are ways of accessing the information in the table where you never actually look at it this way. So for example, if you do print conjugacy classes on G, you get a list of the conjugacy classes of the group. And well, this is kind of a boring group, but anyway, so there are two conjugacy classes. There's an element of order 1, and the length of the minimal Weyl group the minimal representative of the conjugacy class is 0. And there's a levy associated with each element of the Weyl group. I can talk about that at some point later if you want. It's not so important here. The size of the conjugacy class is 1, and the element itself is the identity. And then the second conjugacy class, it's an element of order 2, length 1, the levy is A1. It's just a singleton, and it's the simple reflection 0. And so remember that simple reflections are numbered starting at 0. All right, so let me pause there. So that's the conjugacy classes in the Weyl group of SL2. Now let me pause there and just see if I've got an email from anybody that's not on chat. Doesn't seem that way. Okay. Okay, and so now another thing that we can do is we can look at the cells. It's print W cells of B, I think is the command. So this is such a small example, it's a little confusing, so I won't spend a lot of time on it, but this says that there are 3 cells numbered 0, 1, and 2, and each of them is a singleton. And there's a graph on the cells, and then this information here towards the bottom of the screen. This is the information about cells and tau invariance, and information which enables you to calculate the Weyl group action on the cells. And now, one thing that you can, well, so let's talk about characters of the representations of the Weyl group in characters. So, for example, you can say set T is equal to CT dot trivial. So this notation, CT is this character, this conjugacy class table that I set up, and there are various commands that are going to be of the syntax is CT dot, and this is the trivial character of this group, and it's simply an array of integers giving the values of the character on the 2 conjugacy classes. And so, for example, there's also CT.sign, and then there's CT.reflection. Okay, and let me go back and look and see if, all right, so then when you have a character, for example, let's set R is equal to the reflection representation. You can take the inner product of 2 characters. You can say CT.inner of T and T, for example. That's the inner product in the sense of character theory of the trivial representation with itself, and that's 1. On the other hand, if you do CT.R, that's 0. And so you can, well, in principle, you could build up the character table of a group this way. One of the interesting features is that we don't actually need the character table for what we're doing. We need some aspects of characters, but we don't actually construct the character table. All right, let me pause there and let's see if there are any questions. Anybody? I have to remember there's a 12-second delay, so okay, I guess we're doing okay so far. Oh, actually, I just realized, do I need to scroll down in this chat window? No, it's okay. Good. Remind what type partition? That's an excellent question. So this is something I've been meaning to ask Mark. Partition is what type partition? Partition is just a synonym for an array of integers, and this character, the value of a character is an array of integers, and you should think of it as an array of integers. And I don't know why the software is identifying it as a partition. This is something that Mark will explain to me at some point. Other questions? Okay, so let's do another construction, which is we have the reflection representation, and you can do the symmetric powers of the reflection representation, for example, the second symmetric power of the reflection representation, and that's the trivial representation. So I guess this is kind of a small example. An odd power of the reflection representation is sine, and anyway, so you can calculate symmetric powers of any character. In particular, we're going to apply this to the reflection representation. Okay, so rather than computing anything further with SL2, let me go on to a slightly bigger group where it's a little less confusing because there's a little bit more going on. So I'm going to load the information, SP6. So I'll show you in a minute. I'll go through these things that I've done, but I put all the commands in a file to read in the information for SP6. So G is SP6. And then I said CT is equal to the Weyl W class table, I think. Class table of G. Whoops. Oh, that's correct. So let me go back up above. So I did a bunch of things for convenience, which is I set G, and I set the character table, and I set the block to be the block, the principal block, and I computed the cells and characters and representations and blah, 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 and so on and so forth. So let me go through those one by one and show you. So the way you get the cells is you say set cells is equal to W cells of the block. So for A and let me show you what the cells look like. Actually, let's do this print W cells command first. Okay, so by the way, when we're done with this presentation, somebody remind me to save all of the terminal input and output, so you don't have to, so you'll be able to go back and look. So let's see, so print W cells. So this is a command that's been around for a long time. It prints the cells. So we're in SP6. There are 16 cells, numbered 0 through 15. The first is an irreducible, this is a large discrete series. The second is another discrete series. And then there's a bunch of cells in between. And then the very last guy, I think, is the trivial representation, I believe. And then there's the induced graph on cells. And then there's all of this information at the bottom. And basically this chunk of data right here is what tells you how to compute the action of the Weyl group, the Weyl group representation on this cell. So this cell is 5-dimensional, and there's a representation of W on it called the cell representation. Okay, so that's what the print W cells command does. And this has the same information in it in a more compact form that the software is actually using. So this is a list of the cells, and it's all the previous information in a particular form. So that's how you get access to the cells, and then you can get the characters of the cells as follows. You set chars is equal to cell characters of CT cells. Okay, so for char in chars, do print this char. So these are the 15 characters, the values of the 15 characters of these cell representations. So for example, this first is a 1-dimensional cell, and it's the trivial representation. So is the second. And the third is some 5-dimensional representation of the cell. It's a little bit hard to say what it is, if it's irreducible or what, but it's some 5-dimensional representation. And at the very bottom, this very last cell, that's the sign representation. And these each row is giving you the value of the character on the conjugacy classes. And if you want to see what the conjugacy classes are, here they are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, looks like 10 conjugacy classes. Here are their lengths, and this is the size of the conjugacy classes. So these numbers add up to the order of the Weyl group. And here are representatives, minimal length representatives, in fact, of the conjugacy classes. So, for example, the first one is the identity. 0 is a short reflection. 2 is a long reflection, and so on. Where is the Coxeter element? 0, 1, 2, this very last guy is the Coxeter element of order 6. All right, let me pause there and give people an opportunity to interrupt me and ask questions. Anybody? Let's all not speak up at once now. Okay. So what next? Let's see. So we have these characters, and it's quite clear that these characters aren't all distinct. The same representation appears several times. And so let's, there's a nice thing, you can look at the matrix of inner products of, I think it's CT chars. Oops. So this matrix gives you the matrix of inner products of the cell characters. So there are 15 cell representations. This is a 15 by 15 matrix. And this first row, for example, says that the first and second character in this table are the same. They have inner product 1. And this row here says, well, the diagonal entry being 2 says that the inner product of this character with itself is 2. So this is reducible. And it furthermore says that the characters of cells 0, 1, 2, 3, 4, and 6 are all isomorphic. So 0, 1, 2, 3, 4, 5, and 6 are all isomorphic, as you can see by looking directly at the characters. And so this gives you a lot of information about the cells, and you know, which ones have isomorphic representations and so on. And there's actually, I'd forgotten, there's a command cells table, I think CT cells. That's just shorthand for the same thing. And then there's an augmented version. And this gives you the table of inner products of the cells. And at the end, it tacks on the trivial sign and reflection representation, which is further helpful information. So, for example, you can see that this first cell, because of this 1, that's the trivial character. And this last cell, where is it? Here. That's the very last cell, is the sign representation because it's appearing here, and so on and so forth. Okay. Let's go. All right, so now what do we want to do next? So that's the, let's make the actual representations. So we can say set reps is equal to cell representations of CP cells. So these are actual Weyl group representations. So for example, if we say set pi is equal to reps bracket 0, and we look at it, well, there's some garbage at the top. Oh, I know. If we look at, if you just want to see the operators, you say pi dot operators. So what this says is that this pi is a representation, and it has, for each simple reflection, there's a matrix. In this case, the identity matrix. This is a trivial representation. Let's do a more interesting one. Let's look at this representation number 3 and do pi dot operators. So those are the 3 matrices giving this 5-dimensional representation of the Weyl group. And we can check, for example, that if you take the, if you want the operator number 0, there it is. And if you're concerned about whether I'm making this up, you can check that its square is 1. You could check the braid relations and so on. You can work with these matrices. You can do things with them. Okay, so let's check something for I forget, maybe for so here are these 15 representations, and so these are these 15 cell representations, and what we want to do is, in any given cell, we want to pick out the special representation in the cell. So let me pause again, give people a chance to ask any questions. I don't want to go too fast. So let's take a pause here and let me ask if there are any questions. Okay, well, somebody do me a favor and say something in chat so I make sure everything's working and I'm not talking into the ether. Good, glad to hear it. What are the pi operators? I'm a little confused. Okay, good, glad to hear there's a question. So, so pi is a 5-dimensional representation of the Weyl group. And pi dot operators, bracket 0, this is the matrix by which, this is, I'll write it on the screen. This is the matrix pi of S0, the 0th simple reflection. And so let's set P0 is equal to pi dot operators 0, and let's set T1 is 1 and T2 is 2. So these 3, whoops, sorry, 0, 1, and 2. These 3 operators are the matrices of a 3-dimensional representation. Does operators of pi bracket 0 work as well? That's a good question. Operators of pi bracket 0, indeed. And so, for example, you can check that T0 times T1 times T0 had better equal T1 times T0 times T1. I'm not on a limb here. I haven't checked this before. There you go. Isn't that nice? Letitia or Roger, whoever's ever there, does that answer your question? Good, excellent. What time is it? All right. So there and now. Each cell is pi is a cell representation, and each cell representation contains a unique, irreducible, special representation. And the way you find it is that if pi is a cell representation, you look at pi, the inner product of pi with sim k of the reflection representation, and you take the smallest k, smallest k for which this is non-zero, and the fact is that then pi sim k of the reflection is equal to 1, and the common constituent is equal to the special in pi. All right, there's a little bit of math theory, and so the way let's do this by hand. Let's take this 5-dimensional representation of pi, and let's look at the inner product. Do I have the reflection representation? I don't think so. Set R is equal to CT dot reflection. Dimension of R is failed. R is 3-dimensional. And let's look at the inner product, CT dot inner of, I need the character of pi. So I have the characters, pi characters bracket 3, I think. Yeah, this is the character of pi. So let's set char is equal to char's bracket 3. This is the character of pi, and I can do CT dot inner of this character with the reflection representation. Ah, that's interesting. Really? This has the trivial representation? No, sorry, this has the reflection representation in it. Okay. So this says that this representation is reducible, and it has the reflection representation in it as a submodule, and then a 2-dimensional complement. Let's do another one. Let's see. 4. So here are these the dimensions of these representations. Let's do let's do the 3-dimensional 0, 1, 2, 3, 4, 5. Let's set char is equal to char's bracket 0, 1, 2, 3, 4, 5. Oops. This is the 3-dimensional representation, and let's take the inner product of this with the reflection representation, 0. So there's nothing in common. So let's take the inner product of this thing with ct.sim power R2, if I remember the syntax correctly, still 0. About 3. There we go. So this says that this, let's look at ct.sim power R3. So this is a 10-dimensional representation, the third symmetric power of the reflection representation. And the inner product of this cell representation with this reducible 10 this representation is 1. There's an irreducible in common. So let me pause there. So how do we get our hands on this special representation? We know that it's the unique constituent. You have this 3-dimensional cell representation, which may or may not be irreducible. And you have this 10-dimensional symmetric power, and it's the unique constituent in common. Well, using that information, you can make a projector. So I forget I forget the syntax. Give me 1 second. Oh yeah. So you can do the following. You do special representation. Special representation cell, CT, cells, bracket. Which cell are we in? Which number is it? 5. So it turns out in this case that this cell representation is irreducible because the cell itself, oh no, wait, sorry, the cell was 5-dimensional, right? Yes, I take it back. The dimension of the cell, 1, 2, 3, no, sorry. This is a 3-dimensional cell representation, and the special representation is also 3-dimensional. All right, let me pause there. I'm sure I've confused people, so are there any questions? Blink, blink, blink. Okay. Give me 1 second. I want to refresh my memory about some syntax. So let's go back and look at this 5-dimensional cell. 0, 1, 2. So let's set char is equal to char's bracket 2. And let's do special representation cell. Cells bracket 2. So this is a 5-dimensional cell, but the special representation in it is 3-dimensional. And I wanted to show you something. There's something called the special projector of cells bracket 2, I think we're on. So this is a 5 by 5 matrix which is giving the projection of this 5-dimensional representation onto the 3-dimensional special. So you'll notice that the rank, let's set P is equal to this. The rank of P is equal to 3. So it's a 5 by 5 matrix, but its image is 3-dimensional. And this operation, this is given by summing over the Weyl group to give a projection from a reducible representation onto the special irreducible in it. And this is what's used to compute the special representation itself. All right, so let me pause there. You could compute the pairing of the cell with itself. I could. You could compute the pairing set sigma is equal to reps bracket 2 dimension sigma. This is our 5-dimensional representation, and you could do ct.inner. And that's its character. So you can do ct.inner char, and that's 2. And you're absolutely right. I could, no, wait. Well, that tells me that this thing has 2 pieces. I guess what I could do is, let's see. I have this this 5-dimensional representation, and the special. What's the special representation? Special characters bracket 2. Sorry, I'm not thinking here. Special reps bracket 2. Character, is that what I want? No. Yeah, so look, I'm not going to get this straight, but what I could do, yes, what I could do is I could subtract off I could take the cell representation and subtract off the special, and then, you know, I could decompose the cell representation that way if that's what I wanted to. But anyway, is each column of P a set of cell elements with the same primitive ideal? Exactly. That's what I'm coming to next. So let me just show you that. There's a command print primitive. Well, let me look at that projector again. So excuse me. If you look at this matrix, the first column and the second column are the first column and the 0 and 2, the 0th column 0, 1, 2, and the third column are the same, and columns 1 and 5 are the same. And what that says is that this first column, let's look at these cells. This is cell bracket 2, I think. Yeah, this cell has 5 parameters in it, labeled numbered 1, 8, 13, 20, and 31. And the way you compute the primitive ideal of a representation is you project it onto the special. And two parameters have the same primitive ideal if and only if their image under this projection is the same up to scalar. And so from that, you can compute the primitive ideal information. And we conclude that parameters numbers 1 and 20 have the same primitive ideal. 1 and 20, 8 and 31, and 13 is by itself. So let's do print primitive ideal info. oops, cells, projectors. So this goes through all of the cells and does that computation. So let's look at this information here. So there are 16 cells, numbered 0 through 15, and the next number information. Next number is the size of the cell. So this cell is size 1. The dimension of the special representation is 1, and there's just one parameter in there. Let's look at this number 2, for example. The cell representation is dimension 5. The special is dimension 3. And that says that this array here has 3 entries, one for each basis vector of the special. And then the parameters in the cell are grouped according to their image under this projection representation. So parameters 1 and 20 map to the same thing, 8 and 31, and 13 is by itself. So that's the information that I just sort of did by hand a minute ago, and it automatically does that for you. And so here is a list of the, this gives you the primitive ideals in each cell. All right, let me pause there. Are there questions? Okay, I'll go on. Let's see, what did I want to do next? Oh yeah, so you can look at the special representations. You can say set specials is equal to for cell in cells do special representation cell CT cell. Maybe I did that already. I probably did that already. I can't remember. For pi in specials, do dimension of pi. Oh no, I don't think I did this before. I did the cell representations, but here I'm doing the specials. So actually, let's do for pi in reps. So, excuse me. There's the cells and there's the specials. So you can see that there are these 5s which have the 3-dimensional special and so on. Now it's not so easy to tell from this. There are 3 1-dimensional specials listed here and a whole bunch of 3-dimensionals. How many actually distinct special representations are there? Well, for that, you can do you do sort U. So you let's say set specials U is equal to sort U of the specials, and if U standing for unique. So of these. There are 1, 2, 3, 4, 3-dimensional special representations and 2 1-dimensional. All right, so let me pause there and see if there are any questions. Yes, hello, Gautam. Given a cell, Atlas tells us the Weyl group representation in terms of its character. So you can yes, it gives its character, but you can also get it as operators. So let's show you that. So for example, there's this, that is the character of the 5-dimensional cell representation number 2. Excuse me. And that's the value of the character at the conjugacy classes as listed above. And but you can also we also have this representations number 2 operators. So you actually literally have it as a representation in terms of matrices. Does that answer the question? Well, I know there's a lag, so I'll go on, and if there's a question, I'll come back. So what did I want to do next? The oh, good. Okay. So and so I thought I would look at a slightly bigger example. Oops, H. Here's G. So this is F4, and conjugacy classes long G. Here's the list of conjugacy classes in this group. This is the split group of type F4. And there are, however, 25 classes or something, I forget exactly. And I've computed the cells, of which there are 25. Maybe that's where the 25 was in my brain, I'm not sure. There's 25 cells. And for so I had computed all of this beforehand. It only takes a couple of minutes, but just so we wouldn't have to sit here. So I computed these are the 25 cell representations of F4 and their dimensions. Most of them are rather small, but then there's these interesting 72, 47, and 57. And let's do print primitive ideal info 2 of cells, projectors. I think that's the syntax. So, well, let me just do this first. Cells projectors. So this is the command I gave before. It prints out information about all of the cells. And since these cells are kind of big, this format gets a little bit unwieldy, but let's look anyway. So for example, the second line here says that there's a cell of dimension 6 where the special is of dimension 4. And here are the 4 primitive ideals represented. And here's this cell of dimension 72, the special is of dimension 12. It's a little bit hard to read this, so I wrote a slightly different command to group things differently. So let's look at this big cell here. Where is it? There's the 57. Where's the 72? I think it might be earlier. There's the 72. So this is this interesting cell for type F4. The cell representation is of dimension 72. The special representation is of dimension 12. And that says that there are 12 different primitive ideals. And here are the 72 representations in the cell grouped according to their primitive ideal. You can look at the projectors. What was the number of that cell, by the way? 72. That was cell number 9. So this matrix, it's a 72 by 72 matrix. Let's see if we can get it to fit on without breaks. Not quite. Almost there. Give me a second. Oh, no, it's not almost there. It's very far from there. Never mind. That was a bad idea. Sorry. Yeah, it's a little confusing to look at, so maybe it's not. Maybe I should do a smaller one. What was the? What were these dimensions again? Let's look at this 47 guy. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, let's see if we can get this to display without line breaks. There we go. I don't know if that's too small for people to see, but it's kind of neat. So there's the diagonal, and then anyway, this is this projection operator. The rank of this matrix is 12, and you can look for rows, or excuse me, columns, which are equal up to a multiple. So for example, P bracket 0 is the first column. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like the, oops, maybe it was 10. Whoops. Yeah, so if you look at these two columns, 12 and 0, you see that column 12 is 3 times column 0, and therefore these two parameters have the same primitive ideal, and this multiple, I believe, is essentially the Bernstein degree of the polynomial. All right, let me pause there. Questions? While you're formulating your questions, I'm going to check the trace of this matrix. Anybody want to guess what the trace of this matrix is? Of course, it's 1152, the order of the Weyl group. All right. Where's the W order? Where's the W? That's the size of the Weyl group. I'm not sure why that's true, to be honest, but it's apparently the case. All right, let me pause there. Questions? Okay, well, that's pretty much what I wanted to cover. There's lots more to say, and all sorts of things you can do with the software, but that's probably a good place to stop, and people can experiment and ask me questions, or I can do another webcast sometime. I should have said that the software, let me go back to the window so I can make a note of this. Currently, the software is on the master branch on GitHub. So I'll remind people that if you're using GitHub, you do git pull origin master, and then you almost certainly have to do make. And I always remind people that you should always do make with optimize equals true, and that should compile the latest version of the software for you with all of these this functionality in it. And I'll be putting we'll put a version on the Alice website. Please remember to save the output. Excellent. Okay, so let me pause one last time. Are there any other questions, comments? And if not, well, let's just give people a chance. I will save the output. Any other comments or questions? All righty. Well, I hope people enjoy this. It's I think it's very cool. I'm pretty excited about it. And I'm eager to have people use it and tell me what they find out and ask questions. So have a good day, everybody.